Hello and welcome to the fifth video in the P2 chapter sequences and series. On the screen is a starter question. If you've got time, pause the video and give this a go. But be careful, because there is an easy mistake to make here. Okay, I'm going to go through it on the screen. What you might think initially is this looks like a geometric series. And this looks like R and this looks like A. But not all of that is true. We have a quick look. Our general term is a times r to the n minus 1. Now because this power k is not a power k minus 1, it's not in the correct format, just to pick out a and r. So what I would suggest you do on most of these questions is write out the first few terms and just make sure you know what this sequence is. So here, our first term, when k is 1, is 100 times 2 to the power 1, which is 2. So our first term is actually 200. Our second term is 2 squared, that's 4 times 100 is 400. Our third term, 2 cubed, 8, is 800. So it is geometric, and the common ratio is 2. But as you can see here, a is not 100, a is 200. And the number of terms we want in this sequence is 10 from the number down here. So this is the sequence we want. We want the first 10 terms and we're summing them, but be careful because this number does not represent a. To find a, work out the first few terms, and here it is. And once we know these three, now we can apply our usual formula. For geometric sequences, that is a r to the n minus 1 over r minus 1. Ah, dear. Can I remember what they were? We had a is 200, r is 2, n is 10. So let me just use the question here. This thing equals 200 times r to the power of n minus 1 divided by r minus 1. And if you put that on your calculator, you will get about 10 minus 1 divided by 1, 204,600. Now the second thing to note is that if you've got a scientific calculator, you probably have a button on your calculator that will do this calculation for you. On my calculator, it's on the top right. I need to use the shift button to use it, and it will always be an X on my calculator. I need to use the X alpha button. And I'm not recommending you do this in an exam just to jump to the answer, because at A level, the process needs to come before the answer. To get the answer marks, usually you need to show the method marks first. But it is a very good check if you've got time in the exam to check your answers, put this on your calculator and make sure it agrees with the answer you got using the method that you've shown. So it's worthwhile spending a bit of time getting to know how to do this with your calculator. Okay, this video we're looking at something called recurrence relations. So we've done arithmetic and geometric. We've done sum to infinity for convergent geometric. We've looked at sigma notation. Now we're moving on to a little bit broader, because recurrence relations, although they can include these two, they can also start to generate different sequences that aren't arithmetic and aren't geometric. So let's look at one of these. I hope you recognize this as the Fibonacci sequence. Now if you try and figure out the nth term of this sequence, you're going to have some problems. And that's because there is no common difference. Here is 0, here is 1, here is 1, here is 2. It's not common, it doesn't stay the same. And if you look for the common ratio, here is 1, here is a 2, here is 1.5, here is horrible fraction 5 over 3. Again, it doesn't work. You don't have a common ratio. So this is neither arithmetic nor geometric. Finding the nth term of this is not easy. So not all sequences have simple formulas. They might have formulas, but they're certainly not going to be simple formulas. And in this case, it's much easier to write them, even if they do have formulas, it can be much easier to write them as a recurrence relation. Now recurrence, the word in English kind of just means happening again and again. And a relation, you're connecting one term to the next. So what that means is you're finding more terms using the terms you already know, like you do with Fibonacci. To find the next term, it's much easier, rather than trying to figure out a formula, to use the two terms before it. This plus this gives you the next one. But obviously, in order to do that, you need to know the terms before, and to get those terms, you need to know the terms before that, and all the way back down to the start. So this is the sort of sequence we're going to look at. If you're writing notes, here they are. A recurrence relation defines each term in a sequence as a function of the previous terms. Maybe the previous one term, or the previous two, or even the previous three terms. Here is an example of how we write it. This is the n plus 1 term. So you can kind of think of this as the next term. So the next term equals the nth term, or the term that we are currently on, times 3 plus 2. So this is telling you if you know one term, how do you get the next one? You multiply the term you've got times 3 and add 2. So long as you know the first term. Because if you don't know the first term, you can't get any of the others. So this is not quite complete. The definition for a recurrence relation needs a first term, or sometimes the first 2 or 3 terms. So here we have a full definition for this sequence. And if I want to know what these terms are, I follow the pattern. So let's put in here green, u1 is equal to 4 as part of the definition. Now we also know that the next term, so if I use n equals 1, this will be 1 plus 1, which is 2. So the second term is equal to 3 times the first term plus 2. And the first term here in green is 4. So that's 3 times 4 plus 2 is equal to 14. And then if I want the third term, in this case, for 3 here, n must be 2, 2 plus 1. So the third term is equal to 3 times un, which is 2, plus 2. And u2, I've got in blue on the left, is 14. So 3 times 14 plus 2 is 44. And you can see I can just keep going. But the problem with this is that I do need to keep going. If I want the 10th term, I need to figure out all of the ones before that. It's a much slower process. So 3 times, and put it in purple, u3, plus 2, and 44 times 3, oh, that's 134, I think. Now, as usual, if you've got a calculator, you can speed this process up. You can just put 4 equals, so the 4 is in the memory of your answer button, and then do 3 times answer plus 2, and just keep pressing the equals button, and you'll generate these numbers one by one, and it'll keep going. As I mentioned, there are occasions where you might need more than the first term. So for example, Fibonacci sequence, it reads as the next term equals the one before this, so n plus 1 is 1 before n plus 2, plus the one before that. So if you want the next term, you need to know the term before it and the term before that, which means you need 2 starting terms. u0, and u1. And then with these two, you can figure out u2. So u2, when n is equal to 0, u2 equals u1 plus u0. And u3 equals u2 plus u1, and so on. And you can see, I hope, that you can get some very complicated sequences coming out of this that don't have a very simple pattern in terms of a formula, I mean. It's worth noting that you can write arithmetic and geometric sequences as recurrence relations. So a quick example here. We've got an arithmetic sequence, we're adding 7 each time. I could write that as the next term equals the current term plus 7, where the first term is equal to 5. So we'll start with a 5, and to get the second term, you do the first term, 5 plus 7. And then to get the third term, you do the second term plus 7. To get the next term, this term plus 7. And you can see that this works. Same with a geometric sequence. We can write it as a recurrence relation. The next term is equal to the previous term, or the term I'm on now, times, in this case, 2. Obviously, you can just write that as 2un. But again, we need a starting term. So u1, in this case, is 3. And this recurrence relation with this starting term generates the same sequence as this. But it's quite difficult to use recurrence relations to do the sorts of things we've been talking about so far in this chapter. So what I would normally recommend, if you get a recurrence relation that you can see generates an arithmetic or geometric sequence, it's probably easier just to generate the sequence and then use all the other techniques that we've been talking about so far, rather than using the recurrence relation. Because you can use all the formulas we've talked about so far with these, it's not so easy to use it directly from the recurrence relations. So that's just a sentence here summarizing that. So here is an example of a question using a recurrence relation that is not arithmetic or geometric. I'm going to walk through it. A sequence, A1, A2, A3, they're just using A instead of U, that's okay, because we don't need A to be the first term here. A1 is the first term. So the terms, first term, second term, third term, is defined by this. And as I said, they've got the relation here, but they've also got the starting term. So A1, the first term, is P. Then to get the next term, you take the term you're on, square it, and subtract 1. And this will work for all n greater than or equal to 1. So they're starting with n equals 1, as you can see here, not n equals 0. Sometimes that's quite an important thing to notice. And they've also tagged on where p is negative. First part of the question, show that the third term is p to the 4 minus 2p squared. Now don't let the p put you off, it's just a bit of algebra. We're going to use the same technique as you would as if it had said, show that a3 is 7 or 22 or something. A little bit of algebra, follow it through. A1, they've told us, is p. A2, they've told us, is a1 squared minus 1. So if n is a 1 here, a2 is a1 squared. And a1 we know is p. So that becomes p squared minus 1. And that is the second term of the sequence. Change into green for the next one. A3, which is what they actually want, although we've got to go through a2 to get there, is the one before it, a2 squared minus 1. Now you don't have to put this in brackets, I'm just trying to keep my subscript and my superscript separate and clear. However, I would put the next bit in brackets because this is a two-term thing. We know that a2 is p squared minus 1, and a3 is all of this thing squared minus 1. So be a little bit careful with your algebra here. Now I can't leave it like that because they want us to show that it's this, so I need to keep going until it looks like this. So A3 is, expand this out, p squared squared is p to the 4, minus p squared is minus 2p squared, minus 1 squared is plus 1, and then I still have a minus 1 outside the bracket. So I can see that will cancel with that, and I get p to the 4, oops, minus 2p squared. And that is the form they want. Part B. Given that the second term equals 0, find the value of p. Okay, well we've got the second term here, and they're telling us this must equal 0. So we know now that p squared minus 1 equals 0. So this is a 1 p squared, square root that, and we get plus or minus 1. But they have told us in the question that p is negative, and there's a clue here. They don't say the possible values, it's not plural, the value. So there should only be 1 here. So we know that p is less than 0, therefore p is specifically minus 1. Part 3. Find the sum of this sequence, AR, from the first term to the 200th term. Now, this is potentially quite difficult because we can see, well, we can't see just yet, but there's a suggestion that it's not arithmetic or geometric. And if it's not arithmetic or geometric, then we don't have a formula to find the sum. But I'm getting ahead of myself. Let's just check that it isn't, because it might still be. We've got A1, and that is equal to p, but we've just found that p is minus 1. A2, we were told that is equal to 0. A3, we know is p to the 4 minus 2p squared, and if p is minus 1, p to the 4 is 1, minus 2 times 1, so 1 minus 2 is minus 1. And we can now continue this on using the recurrence relation. The next one is the previous one, so A4 is A3 squared, so that's 1, minus 1 is 0. And oh dear, minus 1, 0, minus 1, 0. And if you keep this going, minus 1, 0, forever and ever. This is not arithmetic, and it's not geometric. There is no common difference. Here we're adding 1, here we're subtracting 1. There's no common ratio. Here we're multiplying by 0, and here you can't multiply 0 by anything and get minus 1. So how do we find the sum of a sequence if we don't know the sum formula? Because we only know these for arithmetic and geometric. The question is kind of, it's got an unsatisfactory answer. If you're like me, you like things clear cut, you like your formulas, but here you just have to sort of figure it out by using a bit of mathematical sense, if you will. I was going to say common sense, but it's not really common. It's a skill that you learn by practice. So if we look at this and we just sort of think about what's happening, we should be able to work out the answer. Not by calculation, but by thinking. If I add the first 2 terms, I'm going to get minus 1. If I add the first 4 terms, I'm going to get minus 2. And every time I add an odd term, I'm going to get an extra minus 1, and every time I add an even term, it's going to make no difference. So I could sort of pair them off a little bit here. For every 2 terms, I'm decreasing the sum. If I add all of these together, I'm decreasing the sum by minus 1. So if I've got 200 terms, then there are 100 pairs of minus 1 and 0. Or you could think of this as there are 100 odd numbers and 100 even numbers. All the even numbers do nothing, and all the odd numbers take it down by 1. So the total sum of this thing, without any calculation at all, we can say the sum of AR from 1 to 200 must be minus 100. I hope you've followed that. One downside of videos is that you can't ask me questions if you didn't. But the next part is very similar. Gone too far? Here we go. Write down the value of A199. And there's a clue in the question. If you see something like this where it says write down, that usually means you shouldn't have to calculate something. Shouldn't involve a formula. Probably there's only one mark available because you don't need to do a process. Just write it down. And that implies you should be able to figure this out. And it comes from what I've already said. The odd number terms are all minus 1. And the even terms are all 0. A199 is an odd number term, so this will be a minus 1. So I can just write it down. A199 is equal to minus 1. And that is our slightly strange sequence question finished. For the rest of the video, I'm going to talk about increasing, decreasing, periodic, and none of these, because these are descriptions you need to be able to use for sequences, and to use them you need to know what they mean. So I'm just going to go through this fairly quickly because they're kind of instinctive. A sequence is increasing. This is any sequence, not just recurrence relations. I'm squeezing two parts of the textbook together in this one video. So any sequence is increasing if every term is higher than the one before it. And it's coming up in this video because it's easy to write this relation using the recurrence notation. So if the next term is bigger than the one before it for all of the terms in the sequence, then you can call it an increasing sequence. Conversely, if every term is smaller than the one before it, or lower, not smaller, lower, then it is a decreasing sequence. And that is all of the terms. It can be periodic, like the one that we saw in the previous example, where the terms repeat in a cycle. So at some point, for some value of k, one of the terms you had previously will come up again in the same sequence. And this is true for all of the terms. That means that all of the terms eventually come back up in the sequence, and you end up with a cycle, a repeating cycle of terms. We can go a step further here because the k is effectively how many terms are in the cycle, and it's called the order or the period of the sequence. The one we had before, minus 1, 0, minus 1, 0, would be order 2. K would equal 2 because there were two terms in the sequence, a minus 1 and a 0, and then they repeated. And lastly, most annoyingly, a sequence doesn't have to be any of these. It might not be increasing, it might not be decreasing, it might not be periodic. Just because it isn't this does not mean it must be this. So be careful, it might not be any of them. To practice these ideas, on the screen here I've got 7 sequences. I'm just going to talk through each one, but if you'd like to pause the video and try and see if you can identify which one is which before I go through it, do that now. So I'm going to start up here. Nice, easy, 2, 3, 4, 5, 6, and so on. This is clearly an increasing sequence, because every time you go to the next term, it will be bigger than the one before it. Moving over to this one, I'll go round like this. This one over here, the next term is equal to the previous term squared, So that might seem like an increasing sequence, except that the first term is a fraction. And if you square a fraction, it gets smaller. And if you square the next fraction, it will get smaller again. And if you square the next fraction, it will get smaller again. So this is actually going to be a decreasing sequence. And if you start with a half, you will never get a term where the answer gets bigger by squaring it. It will always get smaller. So increasing over here, decreasing here. Next one. The next term is equal to the current term plus 3, and I'm starting with a 7. So 7 here, the second term, 7 plus 3, 10. The third term, 10 plus 3, 13. And if each term I add 3, this is going to be very similar to this. I'm going to be increasing by 3 every time, so this must be an increasing sequence. Down here, we've got a geometric sequence, times 2, times 2, times 2. So a is minus 3, r is 2. And if you keep multiplying by 2 with a negative, it's going to keep getting lower and lower and lower. So this is a decreasing sequence. Here I've got a repeating sequence. So it's periodic. And the period is 2. Because I've got a minus 2, 1, and then it repeats. Minus 2, 1, minus 2, 1, minus 2, 1. So there are 2 terms in the cycle. 2 left. Here, the next term is equal to sine 90n. Oh, this is slightly interesting. So we've got n plus 1. So if n is 0, then the first term is sine of 0. This one's a little more complicated. I'm actually going to write these out. So u of 1, so that's when n is 0, is 0. U of 2, so when n is 1, is sine of 90 times 1 is 90. Sine of 90 is a 1. U of 3, so when n is 2, that's sine of 180. That's 0. But be careful here, because if you know your sine curve, you know that this is not yet a full cycle, even though I've got the same term again. Because if I go one further, u of 4, so n is a 3, 90 times 3 is 270, that gives me a minus 1. And then my sequence starts to repeat. I'm back to 0, 1, 0, minus 1. So just because the term came up again didn't mean we were finished the cycle. Be sure that you finish the end of the cycle. Here the order is actually 4, 0, 1, 0, minus 1. And then it repeats 0, 1, 0, minus 1. So this is periodic with an order of 4. Last one, if we go 1, minus 2, 3, minus 4, we can see it's not arithmetic, because to go from 1 to minus 2, you're minus 3. And then if you do minus 3 again, it doesn't get you to 3. It's not geometric for the same reason. 1 times minus 2, times minus 2, times minus 2. No, it doesn't work. There's no common difference, and there's no common ratio. You can also see it's never going to repeat, because if you keep following this pattern, you're never going to get back to 1. It's going to keep going up, down, up, down, up, down, further and further, higher and lower. So this is none of them. It's not periodic, it's not increasing, because this is lower than this and this is higher than this. It's not decreasing either. So color coordinated here, increasing, increasing, decreasing, decreasing, periodic of order 2 and 4 respectively, and none of these. And that's because not all the terms get bigger than the one before it, and not all the terms are lower than the one before it. Sorry, I shouldn't have said bigger, I should have said higher. This is bigger but not higher. And this is bigger but not lower. So I hope that is okay between these 4 terms. You need to understand them and be able to spot when they come in. That is the end of this video. If you've got your textbook for Pearson, you can use exercise 5G and 5H to practice these 2 ideas. Exercise 5G practices the first bit on recurrence relations, and 5H practices these 4 terms: increasing, decreasing, periodic, and none. And perhaps I will see you in the final video for this chapter.